Here's the next example. We want to find the integral. Now remember, the integral represents the area in between the function and the x-axis from 0 to 3 of f of x dx. F of x is a given function. So we're looking from 0 to 3. So we're looking at this area right here. So the area is just given by the number of rectangles we have. We got 1, 2, 3, 4, 5, and 6. So the area is just going to be equal to 6. Now, from 3 to 9 is going to be a little bit more difficult. So we're looking at the area from 3 to 9. So let's break this down, and I'm going to change the color. So we're going from 3 to 4, which is going to be this area, and then from 4 to 5. So 4 to 5, remember, it's the area between the curve and the x-axis. That's going to be this. From 5 to 6, it's the area between the curve and the x-axis, which is going to be this. From 6 to 7, between the curve and the x-axis, between the curve and the x-axis, or the function and the x-axis. So we're looking at this area, okay? From 3 to 4, we have this is the function, that's the x-axis. From 4 to 5, that's a function, that's the x-axis. Function x-axis, function x-axis. So the area is always between the function and the x-axis. And now we just got to count the number of rectangles. We have 1, 2, 3, 4, 5, 6, 7, 8, 9. I'm going to call this 10, even though it's kind of close. 10, 11. And this is like 11 and a half. So I'm going to combine the 11 and a half with this to get 12, 13. So I'm going to approximate this to be about 13. And it doesn't have to be exact. It can be approximate. Okay, so once again, we have 1, 2, 3, 4, 5, 6, 7, 8, 9. We got 10, 11. This is like 12, and that's 13. If we wanted to get more exact, we can just, like use triangles and get the base times height, but I'm just going to count rectangles, and I'm going to approximate. Okay, let's go to the next example. Let a of x represent the area bounded by the graph. So remember, it's, again, the area between the graph and the x-axis. So by the graph, the horizontal axis, which is the x-axis, as we know, and the vertical lines at t equals 0 and t equals x. So basically, these are going to be our limits of integration. So first, we're going from 0 to x equals 1. So from 0 to 1, we're looking at the graph between x equals to 0 and x equals to 1, which the graph is going to be this. So we want the area between the graph and the x-axis, which is this right here. And again, we could approximate. This is 1, and between these, that's 2. So the area is going to be 2. So the integral from 0 to 1 of f of x is going to be 2. Now we want the area from 0 to t equals x, so t equals 2. So let's see the graph between 0 and 2. So we got this graph from 0 to 1. This is 0 to 2. So we want this whole area. We got 1, 2, 3, then 4, and then together we're going to call these 5. So we got 1, 2, 3, 4, and 5. So the integral from 0 to 2, these are our limits of integration, t equals to 0, t equals to 2, of the function f of x equals to 1, 2, 3, 4, and 5. Now we're going from 0 to 3. So look at the graph between x equals 0 and x equals 3. We got here, here, and here. So the integral is always the area between the graph and the x-axis. So we're looking at this area right here. So we have 1, 2, 3, 4, 5, 6, 7, and then this is 1. So that's going to be 8. 1, 2, 3, 4, 5, 6, 7, 8. So the integral from 0 to 3 of f of x is equal to 8. Now, all the f of x's, they always have a d of x, which I did not write over here. So let me switch that. Let me fix that. Lastly, we want the area from 0 to 4 of f of x dx. So this is 0 to 1, 1 to 2, 2 to 3, 3 to 4. And we want the area between that graph and the x-axis. So we're going to go down to the x-axis, find this area. Okay, so we got 1, this is 2, 3, 4, 5, 6, 7, 8, 9, 10, and then this is like half, so 10 and a half. or 10.5. Okay, next example. We want to find geometry to evaluate the definite integral. So first of all, this function here is going to be f of x. So our function is going to be f of x equals to 4. And when it says to use geometry, it means we want to draw this and see what it looks like. So if this is my x-axis and this is my y-axis, I'm going to put some numbers in. We want f of x equals to 4. So f of x equals to 4 is just the line y equals 4. It's going to be a horizontal line where all the y values are 4. So it's going to look like this. And I should probably do that in a different color. So this line here, this is a line, f of x or y equals to 4. Now what do we want to do? We want to find the area. So the integral is the area under the curve between this line, and the x-axis between -2 and 3. So this is -2 and this is +3. We want to find the area between the line and the x-axis, which is this whole area right here. So the area of a rectangle is pretty simple. It's length times width. So the length is 1, 2, 3, 4, and 5. So -2 to 3, this is 5 units. The height is 1, 2, 3, 4, or the width is 4. So if I multiply 5 times 4, then that's going to be 20 square units. Next, evaluate the integral by interpreting in terms of area. So once again, we want to actually graph this and from 1 to 5. So our function f of x equals to 2x minus 5. So once again, let's graph this and see what it looks like. 2x minus 5, it means we have a y-intercept at -5. 1, 2, 3, 4, 5. That's our y-intercept, -5. And I keep forgetting to switch my colors. So this is -5. My slope is 2 over 1. So I go up 2 and over 1. And then I'm going to go up 2, and put a bunch of points in. Okay, I'm going to go up 2 and over 1. Then I'm going to go up 2 and over 1, then up 2 and over 1, and then up 2 and over 1. So this is my line. And the reason I put so many dots is because I know that I have to go from x equals to 1 to x equals 5. 1, 2, 3, 4, 5. So I need my line to go at least up to 5. Now here's what I want to do. I want to find the area from 1 to 5. Okay, the area between the graph and the x-axis from 1 to 5. So let's break down the graph. Okay, let me start highlighting it. From 1 to 2, so I'm looking for x equals 1 to x equals 5, so I'm looking at this interval. So from 1 to 2, the graph looks like this. Okay, this is my graph, and I want the area between the graph and the x-axis, which is going to be this area right here. But that's going to be negative because it's below the x-axis. Then from 2 to 3, 3 to 4, 4 to 5. So that's going to be this area right here. So I need to find out what are both of these areas. And these are two triangles. So we know that the area of a triangle is equal to 1/2 times base times height. So let's do this small triangle over here. Okay. If you look at this y value, that's -3. And from here, we went up 2 and over 1. So this was the line, and we want the area between that and the x-axis. So this area is, the height is going to be 1, 2, and 3, and the base, we're just going from 1 to 2, so it's going to be 1. So it's going to be 1/2 times 3 times 1. 3 times 1 is 3. 3 divided by 2 is 1.5. So the area is going to be -1.5. Why is it negative? Because it's below the x-axis. Okay. Then we are going to keep going from here to here. So let's count. And again, this is an approximation. Let's count our base. We got 1, 2, and 3. Our base is 3. And our height is 1, 2, 3, and 4. So the area is 1/2 times base times height. 3 times 4 is 12. 12 times 1/2 is 6. So the area is going to be 6. Now the total area is the area below plus the area above. So it's negative 1.5 plus 6. So the total area is going to be 4.5 square units. Okay, next one. Let's talk about a Riemann sum. So a Riemann sum is the sum of the area of rectangles that approximate the area under the curve. So basically, in a Riemann sum, you can read all this. I'll go over this in class, but basically, a Riemann sum is going to look like this. Let's say we want the graph of we want the area between x-axis and the graph of y f of x equals 9 minus x squared, which is graphed here, over the interval -1, 2. So we're going from x equals -1 to x equals to 2. So here's what we do for a Riemann sum. Okay, so let's follow me here. I start at my first x value, which is -1, and I go all the way up until I hit the graph, which is going to be this. And then I go to the right, and I come all the way down, and I make a rectangle. Then I go to my next x value. So I'm going from -1 to 2. So my next x value after -1 is going to be 0. So I take x equals to 0, and I go all the way up to the graph, which is here. When I hit the graph, I just go over to the next x value and come all the way down. That's my second rectangle. Then once again, my next value is x equals to 1. So I go all the way up till I hit the graph. I go over to the next x value, and I go all the way down. And I keep going until I hit 2. So when I hit 2, I stop. This is something called a left endpoint approximation. Okay, here's why it's called that. Because this interval is from -1 to 2, or -1 to 0. So I could have picked -1 to go up, or I could have picked 0 to go up, but I'm picking -1. So this is called the left endpoint approximation because I'm picking the left endpoint of any interval and going all the way up to the graph, going right, and making a rectangle. And now for the area, I just have to count the number of rectangles. So I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. 18, 19, 20, 21, 22, 23, 24, and 25. So the approximate area is going to be 25 square units. Okay, so start at -1, go all the way up to the graph until you hit it, then go to the right, come down. Then go to 0, go all the way up to the graph, go to the right, come down, etc., etc. The next example, we'll start this and we'll end this and finish this in class. So we want to find the area under the curve y equals x squared plus 3 from 1 to 4. So our first objective is going to be to sketch as accurate of a graph as possible. Now the curve x squared plus 3, you can graph this on Desmos, but it's going to basically look like this. And I'm doing this by hand, but again, you can feel free to use Desmos for this. So the graph is going to look something like this. And we're going from 1 to 4. So we're going from x equals 1 all the way to x equals 4. So let's just do one rectangle. So my x value is 1, so I keep going all the way up until I hit the graph, and then I go to the right, and I come all the way down. And I count the number of rectangles. This is 1, this is 2, this is 3, and this is 4. 1, 2, 3, 4. Rest in class.